Good afternoon, everyone. I'm Yu Kang, a third-year PhD student in computer science at Shanghai Jiaotong University, advised by He Zhezhi. I'm here to introduce my work, ELSA, an elastic SNN inference architecture for efficient neuromorphic computing. Let's begin from the background and motivation of ELSA. Spiking neural networks, also known as the third generation of artificial neural networks, has been widely studied for their brain-inspired computation paradigm and their potential for high energy efficiency. As shown in the figure, the information of SNN, including input and output, are transmitted by spikes, which neural states are updated temporarily. For classification, each output neuron is assigned to one class, and the predicted class is determined by the neuron that fires most frequently. Recent studies such as SPECZIP, TF, show that SNNs are equivalent to quantized artificial neural networks by using a novel neural model called ST-BF neuron. The ST-BF neuron introduces an additional memory variable called SPECtracer, denoted as ST in this figure. And the ST-BF neuron equals to quantize the root function and support negative spikes. The most attractive feature of SNNs is their exceptional energy efficiency, as illustrated on the left two figures. Different from conventional artificial neural networks, SNN transmits information using binary or ternary spike events instead of continuous valued activations in NNN. As shown by the right two figures, this spike basis of computation in SNN can be realized using simple adders and logic operations in hardware. In contrast, ANN computation requires expensive multiply accumulate units. As a result, SNN can substantially reduce both computational energy and hardware area. Many studies have focused on leveraging the high energy efficiency of SNN, but this leads to a natural question. Can SNN offer benefits beyond energy efficiency? In this work, we found that SNN exhibits an interesting behavior. Their output emerge progressively, as shown on the left. During the early stage of SNN inference, the model first detects nearby vehicles. Then, as the inference continues, more distant vehicles are gradually detected. This suggests that SNN can respond earlier to salient input while allocating more time to harder cases. We call this inference elastic inference. We further qualify the benefits of the elastic inference on ELSA by comparing it with GPU-based QNN baselines. The left figure reports the image classification result on ImageNet, while the right figure reports object detection on COCO 2017. FCR denote first correct response. With elastic inference, some salient samples are correctly classified or detected before the entire inference finishing, as shown the blue bar in these two figures, enabling faster responses and improved adaptive computations. Therefore, elastic inference is well suited for real-time applications, such as autonomous driving, compared to previous SNN accelerators. Therefore, a natural question is, how can we unleash the advantages of elastic inference in hardware? Neuromorphic architecture is a good choice. Compared to GPU, neuromorphic architecture has near-memory computation enabling higher energy efficiency. Compared to data flow architecture, the event-driven computation allows the hardware to compute only when spike occurs, making it much better aligned with SNN inference. Then, the additional only extraction further improves SNN energy efficiency. To further improve the energy efficiency in neuromorphic hardware, minimal memory access is important for the efficiency of elastic inference. In previous neuromorphic hardware, the inner product data flow reads one spike row and the entire weight matrix to generate one memory potential row, leading to high weight buffer access overhead. The outer product data flow reads one spike column and one weight row, but writes back the full memory potential buffer. This causes frequent access to high-precision memory states. In contrast, Gustavson product data flow processes one spike row and fetch the weight rows associated with the active spike position. It updates each memory potential row with a single write back. This reduces both weight buffer access and memory buffer traffic, making it well suited to elastic inference. Then, for the communication in network-on-chip, a just event representation is widely used in previous neuromorphic hardware, such as Trunos, Lohi, Darwin, or PyCore, to enable event-driven computation on hardware. However, each 1-bit spike is encoded as a 32-bit AER packet, including router ID, neuron ID, and tick ID, which can introduce up to 32 times communication overhead on the NOC. This limited the throughput of the elastic inference in neuromorphic hardware. Therefore, a compact AER is needed to reduce the communication traffic. Finally, to obtain the first response as soon as possible in elastic inference, a fine-grained pipeline is essential. As shown in the figure, the spines in CNN and tokens in transformer can be considered as a final computation grain for fine-grained pipeline. Therefore, for an SNN with L layer as n token or spines, the temporal complexity of the first response time in layer-wise pipeline is OL multiply M. In contrast, a fine-grained spine token-wise pipeline allows each spine or tokens to propagate across layers independently, reducing the first response time to OL, leading to n times first output speed up. With this motivation, let's see the ELSA architecture. The top figure illustrates the ELSA architecture, which consists of multiple neural cores interconnected via a 2D mesh NOC. Each neuron core contains a router and 4 PEs. For computation, similar to previous neuromorphic hardware, ELSA takes near SRAM computation, addition-only computation, and event-driven computation as the fundamental techniques. Nevertheless, ELSA also has 3 dedicated designs for elastic inference, including mini-bench spiking Gustavson data flow for raw memory access, bundled AER for communication, traffic reduction, and a fine-grained token spine-level pipeline for fast first response time. This slide shows the PE design in ELSA. Our PE is designed to execute the matrix multiplication operator using a mini-bench spiking Gustavson-product data flow, and ELSA keeps both synaptic weights and neuron states on chip. Each STPF neuron contains a 16-input header tree, a file component and an update component without using any multiplier. This allows ELSA to efficiently support ternary spike computation. Now, let's take a closer look at the detailed computation flow inside each PE. First, each spike is represented by an AER packet with three fields, X, I, YJ, and P. Here, Xi, Yj indicates that the spike occurs at the ith row and the jth column in spike matrix, while P represents the spike polarity, 0 for the positive spike and 1 for the negative spike. ELSA groups spikes from the same row to a mini batch and process them together. Then, the control module in PE uses Xi as a just to retrieve the Xith row of memory buffer and the tracer buffer, and use Yj as the address to retrieve Yj's rows of weight matrix in n-way weight buffer. The address is begin from 0. For example, the negative spike 311 selects the third rows of neural states include the membrane and the tracer, and the first row of the weight matrix. Then, ELSA reads the corresponding weight row and the memory row from the SNN and performs the accumulation in adder tree by adder tree. If the spike is negative, the weight row is first sign flipped before being accumulated. In this way, both positive and negative spikes can be handled with addition-only computation. Then the membrane after integration is sent into the file function theta with spike tracer row. A neural state in STB and generate spikes. Finally, the generated spikes are sent back to control module and then forwarded to the router for inter-PE communication. The firing function theta is conducted by fire components, which comprises of multiple comparator and the gate. Finally, the generated spikes are sent to the update module in STDF neural circuits, which updates the corresponding memory row and tracer row back to their buffers. In summary, with the mini bench backing Gustavson-product, each memory row and spike tracer row are read out and read back to once. Meanwhile, the weight buffer is accepted in a sparse-aware manner. For router design in ELSA, it supports non-matrix operator, including spike softmax, spike layer node, and individual column. The router contains 5 distinct data paths, with a local path chosen from 1, 2 for from local PE to other neural cores, and 3, 4, 5 passes from other neural cores to local PEs. This assignment avoids hardware contention in router hardware. ELSA router supports bonded AER. In bonded AER, the spike from the same spine tokens are bonded into one AER. It has 2 merits. It enables mini bench Gustavson-product in PE and exchange the sharing a spine and token ID to reduce the AER packet size. Okay, after the ELSA architecture introduction, let's see the fine-grained token spine level pipeline. First, let's look at the spine level pipeline in SNN as shown in figure. For conversion with kernel size with 2 kernel size, S1 in layer 2 is data dependence of S1, S2, S4, S5, S6 spines in the first layer. So we compute this spine's first ring to satisfy the data dependence of S1 in layer 2 as early as possible. Therefore, the spine level pipelines calculate the spines in a specific order, as shown in the blue arrows in the figure. The detailed computation display is shown in the slide. We first calculate S1, S5, S6, and S2 in the first layer to enable the S1 in the second layer to start calculation. Then, when the computation of S9, S10 in the layer 1 finish, the S1, S4 in the layer 2 can start computation. Then the computation is S5, and S2. When the computation of S1, S2, S4, and S5 in the layer 2 are completed, the S1 in the layer 3 begin to calculate. With this calculation order, downstream data dependencies are satisfied earlier, enabling earlier execution for subsequent layers. For token-wise pipeline, tokens do not have data dependency to each other. Therefore, we can naturally pipeline the computation at the token level. Then, for the evaluation, we compare ELSA against the 3 different categories of baselines, including elastic SN accelerator, non-elastic SN accelerator, and QN accelerator. The comparison is conducted across 9 benchmarks, covering both CNN and transformer architecture and various diverse tasks and datasets. ELSA achieves SOTA performance compared to other SNN accelerators. And for QN comparison, ELSA also achieves SOTA energy efficiency compared to the same accelerator, sparse hour accelerator and QN accelerator. We also perform technique breakdown for ELSA. The baseline contains fundamental neuromorphic techniques, including near memory, event-driven, and addition-only computation, but without the mini-bench Gustavson-product, spine token-wise pipeline, and bounded AR. With the Gustavson-product, the energy efficiency is improved significantly. With the spine token-level pipeline, the latency is reduced significantly. With BAER, the latency and the energy has also been improved. Finally, let's look at the improvement in ELSA inference. As shown in the figure, compared to the layer-wise pipeline, accurate ELSA design enhances elastic inference with spine token-level pipeline. It enables faster total inference and faster response. In conclusion, ELSA is a near-SRAM data flow architecture specifically designed to exploit elastic inference. Spine token-wise pipeline improves the first time speed, while BAER and mini-bench spine Gustavson-product further improve the throughput and the efficiency of elastic inference. By enabling early response, ELSA is better suited for real-time applications, such as autonomous driving, compared to previous SN accelerators. Thanks for your listening.